Hello everyone, this is Dr. Deeksha Yajurvedi. I'm Associate Professor in Department of Chemistry at Raghunath Girls Postgraduate College, Meerut. In this video, we would be discussing about an interesting topic from the states of matter, that is liquid crystals. So let us know what are liquid crystals. So when we heat up a solid, then before converting into liquid, there comes a mesomorphic state in which the substance is having the properties of both solid as well as liquid. It means a substance which can flow like a liquid, but at the same time it has some degree of ordering in the arrangement of its molecules are known as liquid crystals. So basically they are intermediate between solids and liquids, and they have the properties of both the conventional liquids and those of solid crystals. It means they can flow like a liquid, they have the property of surface tension, viscosity, fluidity, etc. But at the same time, they have the properties of solid as well, like anisotropy, double diffraction, etc. So basically, liquid crystals are those substances which have properties of both solids and as well as liquids. From the figure, it is very much clear that there is a definite arrangement in the solid state and there is a disturbance in the liquid state. But in the liquid crystals, there is some order of arrangement is there, some alignment is there. So it is an intermediate between the solid and the liquid. We can define it as a fourth state of matter, which is then intermediate between liquids and the solids. Now, as we all know that molecules in the liquid state are mobile in three directions, and they can freely rotate about their axes, which are perpendicular to one another. While on the other hand, in the solids, we know that the molecules are immobile and such type of rotations are not possible. So therefore, it is very reasonable for us to suppose that there must be an intermediate state in which mobility and the rotation about the axis can occur. And this intermediate state is known as liquid crystal. Now, liquid crystals, as I told you earlier, have the properties of both solids as well as liquids. So basically, they are mobile. And this property is used in various techniques. I would be telling you further. Now, they possess the property of birefringentness. They also show anisotropy. It means having the magnitude of any physical property different in different directions, like refractive index, dielectric constant, different magnetic properties, viscosity, conductivity, like this. These liquid crystals are very sensitive to electrical and magnetic field. They also exhibit the phenomena based on electrical and optical properties. So, molecules which can exist as liquid crystals are organic. They can be chiral or asymmetric. They can be elongated or rectilinear. They are rigid, and at the same time, they possess strong dipoles and easily polarizing groups. Now, when we study the history of development of liquid crystals, then first such observation about liquid crystals was made by Frederick Renitzer in 1888 when he heated cholesterol benzoate. So cholesterol benzoate is the first liquid crystal which was discovered. This compound exists in solid state, and on heating at about 179 degrees Celsius, it is converted to liquid. But the scientist Rentzer observed that at 145 degrees Celsius, a turbid liquid was formed. This turbid liquid was actually liquid crystal. The name liquid crystal was suggested by another scientist, Otto Lehmann. Now, again, as I told you, this is a temperature dependent property. Now, when we heat up the crystal on increasing temperature, there's a state which is mesomorphic in between the crystal and the liquid, and on further increasing the temperature, the solid state gets converted into liquid state. Now we can characterize liquid crystals on the basis of properties like positional order and orientational order. Let us take this one by one. Now, what do you mean by positional order? It refers to the extent to which an average molecule or a group of molecules can show transitional symmetry, as like any solid substance shows. It means positional order refers to the tendency of molecules to remain intact in their position, as like in solid state occurs. The second characteristic is orientational order. It represents the measure or the tendency of molecules to align themselves along the direction on a long range basis. So on the basis of these two orders, that is positional order and orientational order, we would be further classifying liquid crystals into various types. And I would be telling you about them in upcoming slides. So let us classify liquid crystals. This classification can be done on the basis of, first of all, properties like temperature. These liquid crystals can be temperature dependent. So such type of liquid crystals which are dependent upon temperature are known as thermotropic liquid crystals. As the name suggests, such liquid crystals which exhibit a change in phase transition as the temperature is changed. So they are temperature dependent liquid crystals. On the other hand, those liquid crystals which exhibit such phase transitions as a function of both concentration as well as temperature. Concentration of solvent in which the liquid crystal molecule is kept. So such type of liquid crystals are known as lyotropic liquid crystals. And the third category is metallotropic liquid crystals, means those liquid crystals which not only depends upon temperature and concentration of solvent, but at the same time it is also dependent upon the composition, including both organic and inorganic molecules. So this was the first classification of liquid crystals which was done on the basis of property. It means they can be thermotropic if the temperature is changed. They can be lyotropic if they depend both on temperature and concentration of solvent. And they can be metallotropic if they depend on concentration of solvent, temperature and composition also. Now, thermotropic liquid crystals, they are formed by heating of solids to a particular temperature. Like I gave the example of cholesterol benzoate. So it is an example of thermotropic liquid crystals. On the other hand, lyotropic liquid crystals are formed by the action of certain solvents on the solids. Generally, these are two-component system where amphiphilic compound is dissolved in a solvent. They can be lamellar in shape, they can be hexagonal or cubic. For example, soaps. All the soaps are basically lyotropic liquid crystals. Now this is a figure which is very easily depicting how on heating the crystal changes to liquid crystals, and on further heating it gets converted to liquid. And the reversible phenomena also occurs. Liquids on cooling down again passes through the mesomorphic state, that is liquid crystal, which on again cooling changes back to crystal. Now these liquid crystals can now be further classified on the basis of positional order and orientational order into three main categories: nematic, smectic, and columnar or cholesterol. So we would be discussing about these one by one. Now, as we can see, the first type of liquid crystal is nematic phase. These are known as phases. It means thermotropic liquid crystals, which are temperature dependent liquid crystals. They can be classified on the basis of positional order and orientational order into these four types. They can be nematic, which are having the shape of nematodes like. Then they can be smectic. Smectic words arises from soap like. They have some similarity like that of soaps. And the third one is cholesterol or cholesteric phase. And the fourth one is disc-like, which is known as dystotic phase. So we would be taking them up one by one. Now, as we can see that the name suggests, smectic liquid crystals are those which are soap-like or greasy in nature. So they are more closer to the solid side and less to the liquid side. So they have the proper orientational order, but a positional order is a little bit disturbed. So the molecules which are known as mesogens, they have both positional order as well as orientational order. Orientational order is perfect, but a positional order is little bit disturbed. Now, there is no such overlap of molecules in such type of smectic liquid crystals. They are not at all oriented by magnetic field and they are bidimensional crystals. Now, these smectic crystals can be further classified into two categories, smectic A and smectic C. I would be taking them in the further slides. Now, these smectic crystals are of pharmaceutical importance. They are very important in pharmaceutical industry because they form ternary or quaternary complexes containing a surfactant, water, or non-polar additives. So they find use in pharmaceutical fields. Now, as the name suggests, I told you smectic liquid crystals are those which are temperature dependent and they are soap-like. You can see these molecules have good orientational order, therefore they align themselves approximately parallel to the axis and they tend to arrange themselves in layers. This is an example of smectic liquid crystals. I was talking about the difference between smectic A and smectic C. Now, if they are aligned themselves to the axis, just parallel to the axis, then they would be known as smectic A. But if they've little bit tilted and making an angle to the axis, then they would be known as smectic C. Example of smectic liquid crystal is like ammonium oleate. It is an example of smectic liquid crystals. Now coming to the second category of liquid crystals which are thread-like or nematode-like, that's why they are known as nematic liquid crystals. Now in these liquid crystals there is no positional order. That is, positional order is totally lost. But they have a little bit orientational order. Molecules are parallel to each other and they are more towards liquid-like. Smectic crystals or liquid crystals were very much similar to solid side, but these nematic liquid crystals, they're very much nearer to liquid state. Now molecules here are mobile in all the three directions and they can rotate about one axis. Unlike smectic liquid crystals, here overlapping of molecules can occur and they have comparatively low viscosity and are less temperature sensitive. These are the nematic liquid crystals which are used in LCD, that is liquid crystal displays, all the electronic devices like watches, like calculators, like TVs, laptops, mobiles, they all are employing these nematic liquid crystals. Example of nematic liquid crystal is one of the most easiest and typical example is para-azoxyanisole. So these are more close to the anisotropic liquids as I told you earlier in comparison to smectic. They have low viscosity and they can flow very rapidly because they show the property of liquid state more. And in polarized light we can see them to appear like moving threads. Examples can be para-azoxyanisole, para-azoxyphenitol, para-methoxycinnamic acid. Now coming to the third one, that is cholestric liquid crystals. They are also known as chiral nematic liquid crystals. Arrangement is almost similar to smectic and nematic, but the difference is that they have an helical structure. The structure is helical and there is a twisting repetition of nematic phase, like the phase changes after 2-3 layers, again the structure is changing. So since they're having a twisting which is known as pitch or the 360-degree turn, after rotation of 360-degree turn, again you would be having the same layer. So there are various layers in cholesteric liquid crystals. They don't have any type of positional order. They don't have any type of orientational order, but they are highly temperature sensitive. And that's why these cholesteric liquid crystals are used as temperature sensors. Now you can see that in this layer and this layer, there's a difference. The first upper layer and the first lowest layer. After the first of all, the orientation becomes in this side, then again parallel, then this side, and again this. So this layer and this layer, topmost layer and the bottommost layer, they are becoming similar after the rotation of 360 degree. And this angle or the helical which is used is, let me show you with the help of pen. This, see, this is known as pitch or the lambda. Means the distance between the topmost layer and the bottommost layer, it is known as lambda, that is the pitch, and this is 360 degree turn. 360 degree turn is taking place. So this is cholesterol liquid crystals which are used as thermal sensors. As I told you, they show a layer structure, and these layers are much thicker than smectic or nematic, like 500 to 5000 molecule thicker than smectic and nematic. The first substance in which such type of mesomorphism was observed, as I told you, was cholesterol benzoate. Now, since we have studied about the classification of liquid crystals, so I'm very quickly switching to the application part. These liquid crystals can be found both in the natural world, like tobacco mosaic virus. It is an example in which this liquid crystal is seen, and then in technological applications also. Most of the contemporary electronic displays which we use today, like laptop, mobile, all the gadgets, they are using the properties of liquid crystals. Lyotropic liquid crystalline phases, they're abundant in living systems. Many proteins and cell membranes, they all are liquid crystals. All the soap solutions, detergents, they all are liquid crystals. See, with the help of this diagram, we can see how the alignment and the orientation is seen. In the nematic, you can see there's a uh, loss in positional as well as orientational order. Positional order is completely lost. There's no specific position of all the mesogens, but a little bit orientational order is there. In comparison to nematic and smectic, there is a positional order as well as there is an orientational order. But in smectic A, all the mesogens are aligned parallelly to the axis Z, but in smectic C, they are making an angle, they are tilted to an angle theta. That's why they are known as smectic C, and this is known as smectic A. This is a very beautiful diagram in which, on the basis of temperature, all the four types of liquid crystals are seen. This is the crystalline phase, means all the solids. Then this is a smectic, this is nematic, and this is again the liquid. The journey from solid to liquid via liquid crystalline state, that is smectic and nematic. Again, you can see there's in positional order and orientational order in smectic. In nematic, positional order is lost and orientational order is also lost. And this is the pile of cholesterol liquid crystals. You can see after the round of 360 degree, again this layer and this layer becomes same. Again after the round of 360 degree, this layer and this layer becomes same. With this diagram, we can very easily understand the basic differences between all types of liquid crystals. I'm just showing you these slides just to give you a definite clarity about the difference between types of liquid crystals. Last part, coming to the applications part, they found an important application in pharmaceutical industries. As I told you earlier, they can be used as various pharma drugs, as the names are mentioned, and they can also be used as solubility enhancers. Now, next uses, they are used in flat screen television, laptop screen, switchable windows. The most common application of liquid crystal is liquid crystal displays, like in projectors, in watches, mobiles, calculators. Uh, there has been a revolutionary change in the technology after the introduction of liquid crystals. Then liquid crystal thermometers can be used. They can change the color when the temperature changes, as you can see from the figure. As the temperature changes, liquid crystals show the color. So they are very much friendly and find an application as liquid crystal thermometers. again in the form of digital calculators. In the next video, I will be telling out how these display numbers are made on the basis of 7 segment cell. You can see the first segment, second, third, fourth, fifth, sixth, seven. So here, if this one is missing, the number becomes 9. If these all are missing, number becomes 1. So on the basis of 7 segment cell, this works, and like this, liquid crystals also find use in digital calculators. Then another important application is of optical imaging. In this technology, a liquid crystal cell is placed between the layers of photoconductor, and when the light is applied to the photoconductor, conductivity of the material increases. As a result, an electric field is developed which corresponds to that the intensity of the light, and the electrical pattern which is transmitted by the electrode, it enables the image to be recorded. So in this way, liquid crystal is also used for optical imaging and recording. Then we have some another applications also, like liquid crystals can be used for non-destructive mechanical testing of materials under stress. They can also be used in medical industry. For example, transient pressure transmitted by a walking foot on the ground can be measured with the help of liquid crystals. So with the day by day, new properties and new types of liquid crystals are being investigated and researched, and that's why they're gaining importance in industrial and scientific applications. Thank you so much. I had tried to give you an insight about the liquid crystals, their classification, their properties and application. I hope that you find this video useful in having a better understanding of liquid crystals. Thank you so much.